this video, we're going to discuss the first unit of basic calculus, which is limits. Let's have a review first of some of the terms that will be repeatedly used in our subject. Let's first start with function. Now, what is a function? A function is a relation for which each value from the set of the first components of the ordered pair is associated with exactly one value from the set of the second components of the ordered pair. This is basically talking about the x and y values in the ordered pair. So meaning one specific value of x would correspond to only one value of y. So that is it could be a one-to-one relation or a many-to-one relation. Now take note that there are different ways for you to represent a function. It can either be an equation. So let's say f of x is equal to x squared. So that's a representation of a parabola or a quadratic function. When it comes to graphing, we can write it as, or we can show it as a graph. In this case, a parabola opening upwards. Or it can also be by table of values. So we can say x, and then we can say y, or simply f of x. So we can say when x is 1, y is 1. When x is 2, y is 4, 3, 9, and so on and so forth. So these are some of the ways in order for you to show or to represent a function. Take note of how these representations, because later on it will be useful when it comes to understanding the concept of limits. Now let us first consider the function f of x is equal to x plus 3. If you could remember, there are different operations on functions, and this time I would want us to focus on the substitution or the evaluation of a function. So if you're asked what is the value of f of 3, so it's basically saying evaluating the function at 3, or sometimes we say what is the value of function at x is equal to 3. So they mean the same thing, okay? So in this case, I would write f of x is equal to 3 plus 3. Sorry, this should be 3. So therefore, f of 3 would be equal to 6. So the value of the function at x is equal to 3 is 6. So that's how you evaluate it. Now let's consider the function f of x is equal to x cubed minus x squared all over x minus 1. Now, what is the value of f of 1? So again, we evaluate and we say f of 1 is equal to 1 cubed minus 1 squared all over 1 minus 1. Now this becomes f of 1 is equal to 0 over 0. So therefore we say that f of 1 is indeterminate. Now remember, when we say undefined, we mean that the denominator is a 0 and the numerator is a non-zero. It could be either positive or negative. But if it's indeterminate, it's the numerator and denominator that is undefined. In this case, you just have to remember that there are different forms of indeterminate, but what we're focusing on is 0 over 0. Now that so what if it's 0 over 0? So actually, it will be our lesson for today will be heavily correlated with the first video that I showed to you guys with regards to the introduction to calculus. All right, so here's what we're going to do. We are going to look at the behavior of the function, but before we go ahead and do that, I will show to you that this function can actually be simplified. If you can look at the numerator here above, we could say that we could factor out what is common, and that is x squared. So what's left is x minus 1, and the numerator is just x minus 1. Now you might be tempted to just cancel out the x minus 1s in the numerator and denominator, but don't do that because this is how the function is defined. So don't cancel it out. But then again, this simplification actually is helpful for us. And why is that so? Now remember that if you cancel this one out, you got x squared. X squared is actually a parabola, right? If you go ahead and graph that, it looks like this. Now, why is there a dot here? Remember that when x is equal to 1, it becomes indeterminate. The value of the function is indeterminate. If you could remember your lesson in general mathematics, whenever there's an indeterminate in the function or whatever value that makes the function indeterminate, when you show it in a graph, it shows as a hollow point, so which is this case here. Now, what we're going to focus is the concept of limits. If you could remember the Zeno's paradox, it was talking about how travel is nonsensical because of the concept that whenever we go to a certain place, we can always um, indefinitely or like actually infinitely cut the distance by half infinitely. But then again, if you could remember as well in the context of Zeno's paradox, even if we infinitely cut or even if we infinitely add small portions of a distance, it would add up to a finite distance. And we are going to focus or we are going to translate that context here in the limits. How do we do that? Now, remember that again, at x is equal to 1, the function becomes indeterminate. But when we talk about limits, we're not gonna focus on what happens to the function at x is equal to 1. We're not going to talk about what happens to the function at a specific value of x. Rather, we are going to talk about what happens to the function as we go closer to the value of x. All right. So this is how it's going to be illustrated. So when we say what happens to the value of the function, we just mean what happens to the value of y, because remember y is equal to f of x, and the value of the f of x is really dependent on the value of x. Okay, so as we change the values of x, there's always a change in the values of y depending on what kind of function that is. So in this case though, as we go from the left, or actually from the right of 1, so if you go ahead and change the values for 1, for the values of x, as you can see the values here in the table of values, it goes closer and closer to 1 from the right. Okay, these values are always bigger than 1. Now what happens to the values of y? In this case, there's also a change. If you look at it, if you look at the visualization through the graph, the value of y is going down, right? So it is also changing, as you can see here. So it is also going to a certain value. As x is approaching 1, the value of y is also approaching a certain value, right? Which is, in this case, can be very obvious already. But then again, let's go ahead and talk about what happens as we approach the value of x is equal to 1 from the left. So as we go ahead and go from left to right, going to positive 1, there's a change in the values of y as well. So in this case here, the values of x are approaching 1 from the left, meaning these values are all smaller than 1. But then again, as you look at the values of y corresponding to the changing values of x, it is also going to a certain value, and where it is going to is actually 1. But you have to remember that at x is equal to 1, the value of the function is indeterminate. It does not, you know, it does not exist. But then again, when you look at the function, the behavior of the function, it seemingly is going to 1. Okay, but when you reach your destination, which is x is equal to 1, y has no value, or the y is indeterminate. Our focus in limits then is not the uh, not the value of the function to 1. So does that mean then that for the function for the function given a while ago, f of 1 is equal to 1, just because it behaves that way? The answer is no. F of 1 is still indeterminate. Even if it seemingly goes to 1, it's still indeterminate. So we can say though that as x approaches 1, the value of the function approaches to 1 as well. Okay? So as we go closer and closer to 1 from the left and the right, when it comes to the x value, the value of the function or the y values goes to 1 as well. So this is the concern of the limits. The limits is not concerned on the value of the function at a certain value of x, which is illustrated here at 1. It's not really concerned at this value, but rather it is concerned on the behavior of the function as x approaches to 1. So as we go closer and closer to 1 for the value of x, what happens to the value of y? In this case, again, it goes down there and it goes up here. And it goes to a certain value and it seems to be it's 1. So that's the main concern of the function. So let's just say, again, our illustration a while ago for the function. So the correct way of showing the limit of function, we say the limit of the function f of x as x approaches to a is equal to 1. What does that mean? The limit of the function, or the value to which the function approaches to, is L as we change the values closer and closer to a. All right, I'm gonna repeat that. The limit of the function is concerned as to how the function behaves, or where does the function go, seemingly go, where does the value of y seemingly progresses to as we change the values of a. In this case, as you can see, as we move the values of x, so the dots that you see here are x values. As we change the values of x closer and closer to a, what happens to the values of the y here? So the dots here are the y values. The y values are also going closer and closer to L. And L is then the seemingly end value as we go closer and closer to A. Okay, you have to remember that this, I will have to be very redundant on this one because it is applicable when it comes to the next units of our discussion in derivatives and antiderivative derivatives, that the focus of the limit of a function is its behavior and not its end, um, its end value. Okay, uh, what I usually say to my class before is that it's the limit of the function is talking about the climb and not the peak. Okay, how does the climb uh, look like? Okay, it's not really the peak of the mountain, so you have to always remember. So let's try to evaluate uh, limits here. Okay, so when we evaluate limits, there are different ways of doing it. There is really a shortcut, but before we go to the shortcut, let's try to identify how the long cut goes, if there's such a term. So we can either go ahead and make table of values or go ahead and graph the function to show the behavior of the function. In this case, I'm gonna go ahead and choose to graph the function. This is the function in this case is this one here, right? Again, it is the limit of a function as x approaches to a. Okay, so in this case, a is 2. So if we go ahead and graph the function, this is just a rough sketch of the function here. Now remember that this is 2. So we know if this is 1, the value of the function is 1. How do I know that? You evaluate, okay? So how does the function behave as x approaches to 2? Okay, so from the right of 2, the values of the function are going closer and closer to which value here? So as you can observe, it goes closer and closer to 4. So we then say that um, this is equal to 4. Why is that? Again, as we change the values of x closer and closer to 2 here, the values of x squared, or the function itself, or the graph, behaves as though it goes to 4. Okay? Again, we are not up for what is the value of the function at x is equal to 2, but rather how the function behaves or how the function changes as we go and change the values of x closer to 2. Okay, now let's have this kind of function. Remember, in your general mathematics, this is what we call a piecewise function. Now again, it will be very useful if you go ahead and graph the function. So let's go ahead and graph it. So how do you graph a piecewise function? Remember that we look at how it is described in its subdomains. In this case, we have two subdomains here. So it is x squared if ever x is not equal to 1. It means that if ever we have x is equal to 2, 3, -5, whatever other numbers than 1, it is x squared. What is the graph of an x squared? That is a parabola. Therefore, I can go ahead and say that this is positive 1 here. So when I make a parabola, there's nothing there. Okay? Because it's only a parabola whenever it is not equal to 1. What happens to the function if ever it's equal to 1? It is -8. So when we say -8 here, there is a point below. So therefore, we have a piecewise function that looks like this, a parabola, which has a hole at x is equal to 1, but then again, it has a point at -8. So let's just go ahead and evaluate then. Um, how does the function behave as we go closer and closer to positive 1? So again, going from the right, so if we go ahead and draw, lines, remember that when we evaluate a function itself, like, the x squared as it's, when we evaluate x squared to 1, if it's just, if it's not a piecewise function, we know that the value of the function should be 1. Now, it also behaves that way, that as we change the values of x closer and closer to 1, it seemingly goes to positive 1 for the value of y. But we all know that the end goal, or like the peak in this case, is actually -8, right? Like the finish line. But then again, the track through which the function runs seemingly goes to 1. So therefore, we say that the limit of this function, this piecewise function, as x is approaching to 1, is 1 and not 8. Okay, so what are the implications of the two examples? So the limit of the function f of x as x approaches to a may still exist even if f of a is undefined, just like in the first example a while ago, that the function becomes 0 over 0, undefined or indeterminate, there would still be a limit of a function. Okay, but it's more clearer when it comes to indeterminate, as shown in the example a while ago. Later on, I will show to you what happens if the function becomes undefined at a specific value a. How does it behave as it goes closer to that? That will be our next topic. Now, it can also exist if ever, so we say that f of a is indeterminate. So the function may still exist, which is this one, or it could also be equal to the limits of f of a is also equal to the limit of f of x as x approaches a. So like the behavior and then the end goal, or like the peak, is just the same. Okay, so in this case, the behavior and then the end goal is not the same, or we can also say that not equal to the limit. So there is a value, a certain value for f of a. Now they're not equal to each other, but then again, the limit of the function, or there is still a visible behavior of the function. So this one. So those are the implications of the examples a while ago. You will have to remember these because it will be useful as we go further into the discussion. Now let's have one example. So determine if the limit of the function f of x exists as x approaches to 0, and the function is this one here. Okay, so again, because it's a piecewise function, it will be wise for us to graph. So let's go ahead and graph the function here. So first it says that for values, or for x values bigger than 0 or 0, the function is just 1. So when we say x is equal to 1, then therefore y is just 1. X is equal to 2, y is just 2, so and so on and so forth as you go further to that direction. So therefore, it actually is a horizontal line from from 0 to positive infinity for positive infinity. Now, how about for this one? How do you graph that? It says that it's 0 if the values of x are less than 0. So meaning not including 0. Okay? So if it's negative 1, negative 5, negative 100, the value of the function is still um, 0. Let me change the color so that you would see. So going to that direction. And this case, this will be a hollow because it is um, a strict inequality, meaning 0 is not included. So if you go ahead and do a vertical line test, there would always be just one value or uh, one point in the function that is touched by the vertical line. So still passes the vertical line test. So let's just go ahead and determine the behavior of the function then. So as you can see, uh, let's first identify the behavior of the function as we go closer and closer to x from the right. Sorry, 0 from the right. So meaning values that are going lesser and lesser uh, because they are bigger than 0. So going here, as you can see, there is a constant behavior, right? So from the right of 0, the function seemingly goes to 1, or actually is consistent. It goes to 1. So I'm going to go ahead and write that here. Um, x and y. So let's just say 5, 4, 3, 2, 1, even 0.5. These values, because these are all bigger than 0, these would always be 1. So seemingly, the function goes to 1. Or actually is on 1 and is consistently on 1. But when you look at on the other side, as we go 0 from the left, or values that are lesser than 0 and becomes bigger and bigger, so looking at the illustration, it stays at 0, right? So if you make a table value for that, let's say like -5, -4, -3, -2, -1, -0 0.5, because these values are lesser than 0, and therefore the values would always be 0. Okay? So what then does this imply about the limit of the function? From the right, it goes 1. From the left, it goes 0. This case, we say that the limit of the function does not exist because the behavior of the function the behavior of the function as we approach x from the left and from the right is not the same. So they do not behave the same. So they do not go to the same quote unquote peak. Okay. So they do not go to the same goal. So this is when we say that the value of the function does not exist because the left side limit and the right side limit are not equal to one another. And so therefore, it's important for us to identify and talk about one-sided limits. When we have an equation that looks like this, we have a positive, it means from the right. Okay, so when we go ahead and graph that, let's just make a rough sketch. If this is value of a, when we are only asked to find the limit of the function as x approaches from the right of a, it means that we are going to test values that are on the right of a. Okay, plus meaning it's on the right, right? And then similarly, if we talk about the value or the limit of the function as x approaches from the left of a, we are going to test the values here. Okay, bigger values that are increasing but are lesser than a. Okay, so these are the one-sided limits. So it's important then for us to identify the one-sided limits. So the values of the function as x approaches from the right of a or from the left of a. So using, in this case, let's have another one. Uh, Using graphing of the function or the graph of the function or table of values, determine if the limit of f of x exists as x approaches to 0. So again, I'm going to show to you left-hand limit and right-hand limit. Okay, so we are going to first do graphing. All right, so if you graph, you have to make sure that you understand, again, the subdomains of the function. So it says that it is x squared, meaning a parabola, if x is greater than or equal to 0. Okay, so what does that look like? So I'm gonna use a different color for this one. So 0 is included, so we know that's a parabola, right? But it's only half of the parabola because it's only a parabola from 0 to positive infinity. So meaning it goes that way. How about this one? It says it's 0 if x is less than 0. So meaning it's a constant function. So remember, a constant function is when we don't have variables, right? So here it just a hollow for that and goes to that direction. Now my illustration is not uh, accurate, but it kind of looks like that. It behaves that way. So let's talk about the left-hand limit of the function. So what is the limit of the function f of x as x approaches 0 from the left? So meaning we're focusing going to that direction. Okay, now remember, if you make table of values for that, okay, let's just make table of values. If we have -5, -3, -1, negative 0.5, the values of the function would always be 0 because these values, x values, are lesser than 0. Okay, so seemingly the values of the y values is at 4, at 0, and it stays at 0. So meaning we say that the limit of this function is 0. Now how about the limit of the function f of x as x approaches 0 from the right? So we look at the functions here, the function here. So as you can see, there is also a change in the values of the function, right? So if we're gonna make like certain values, like make up values here, x and y, from the right. So when we say, like, for example, 3 to 1, okay. So the value of y here, when we evaluate that, because these values are bigger than 0, we are going to use this function here. So this becomes 9, this is 4 and 1. And if this is 1/2, this becomes 1/4, and so on and so forth. As you can see, the values of the function goes lower and lower, and it kind of goes to 0. If you make these values smaller, like for example 1/8, that becomes 1/64, and that's a lot of zeros if you evaluate that as a decimal. So therefore, the value of the function seemingly goes to 0 as well. Now, because the left-hand limit and the right-hand limit are equal to one another, we therefore say that the limit of the function f of x, which is this piecewise function here, as x approaches to 0 from both directions, is equal to 0.